Um, so in this video, we're going to discuss magnetic force on current, moving charge. So in the previous video, we learned that current, electric current, that moving electric charge produces magnetic field. And using that property, you can make an electromagnetic coil. So now what happens if you have a moving charge in an external magnetic field? Those moving charge in external magnetic field, the moving charge feels magnetic force. Just remember though, it's not that just any electrical charge feels the magnetic force in the magnetic field. The electric charge has to be moving, and it's not just moving. They feel the greatest force when electric charge is moving perpendicular to the external magnetic field. Let's say if electric charge is moving parallel to the magnetic field, then this electric charge feels no force, no magnetic force. It's just going to keep going with the same speed in constant speed and no change in direction. But if the electric charge is moving perpendicular to the magnetic field, this electric charge feels the maximum force from due to the magnetic field, and it turns. The magnetic force that's applied on electric charge is always applied perpendicular to these two planes, these two directions. So let's say the electric charge, magnetic field, then let me see, current, magnetic field. So you use the right hand rule. Current is the direct. So you look at, this is your right hand. It's not my left hand. This looks like right to you, so I'll try. Makes sense. I hope it makes sense. It's actually this is my left hand, but I'll try it. The direction of a current is this on your right hand, and then the, you curl up the fingers, right hand fingers, and that's going to be the direction of your magnetic field. And your thumb, your right hand thumb, will show you the direction of a force applied. So you can see that whenever you have two lines, that makes a plane. So perpendicular to that plane that's made of two lines of the current, and a magnetic field, then it's either this direction or this direction is going to be the magnetic force applied on the moving charge. Again, does the stationary electric charge in the magnetic field, does it feel the magnetic force? If so, which is the direction? No. If electric charge is not moving, this electric charge will not feel any magnetic force, even how strong the external magnetic field is. When the electric charge is moving along the external magnetic field, does this electric charge will be accelerated? No, it won't. If it's moving parallel or anti-parallel to the external magnetic field, this moving charge, electric charge, will not feel any magnetic force. So therefore, no acceleration. So how about if the electric charge is moving perpendicular to the external magnetic field? Does this electric charge feel accelerate? What happens to its speed? Correct answer is yes, it accelerates, but the speed, there's no change in speed. It only changes its direction. If you have a force applied perpendicular to the motion, what happens to the speed? no change in speed. Only direction changes. So let's summarize all these ideas. Maybe I'll show you on the whiteboard first. So moving electric charge. In magnetic field. Magnetic force applies. And the direction is perpendicular to the motion of a charge, of moving charge. So let's see. In if let's say in the textbook there is a electron E minus is coming. So I'm going to change the direction. There's a bar magnet. It's okay. Okay, there's a bar magnet. I think it's because of this. That's all right. So let's say the bar magnet have, I'm going to change the direction. North, let's put this to be north and south. So I changed the direction of magnetic field from the textbook picture, but it's the electric charge that's moving. Then I'm going to use the right-hand rule. In this case, electric charge is negative, right? This is negative. This is electrons. So then imagine that means that current, this is the direction of a current. Current is defined by the positive charge. So that it's going to be oppositely moving, and you curl up your right finger to the north and south. So this one, the electric charge will go, this electrons, let me see, purple then, will go downward. It's going to be going down. Inertia is going to take over, so it will be down. So the force will be, this is going to be the magnetic force applied on the electron, downward. You see that current? So the current is this way, I, and the magnetic magnetic force, magnetic field is north to south, this way, north to south. So therefore, the magnetic force will be downward. um, no force, no magnetic force when electric charge is moving parallel to the magnetic field. And then there's going to be the maximum magnetic force when electric charge is moving perpendicular to the magnetic field. So in between, if you have a, so what it means is that any of the perpendicular component of the electric charge, motion of electric, direction of motion of electric charge that's perpendicular to the magnetic field. So any component. So let's say you have an arbitrary angle, right? Like this, and then an arbitrary angle. So only this part that's perpendicular to the magnetic field, that's what's going to feel the magnetic force. All the components that's parallel to the, so the all the component that's parallel in this direction will feel no magnetic force. So only this part of the motion relative to the magnetic field feels the force. And the direction of a force is going to be perpendicular. So whenever you have a motion of electrons or the charge and then a magnetic field, it makes a plane. That's the plane that's going to be. If you have two lines anywhere in a space, that's going to be a plane. And then magnetic force is always applied perpendicular to that plane. So when you have a motion, so let's review it. You're moving in direction. This is your direction of motion, right? Of a charge. Then if you have a force always applied perpendicular, always perpendicular, then you're not going to have any change in speed, no change in speed. There's no way that you can accelerate, go faster, speed up, or decelerate, go slower, because the force is perpendicular to the motion. If any component that you have a little bit of a parallel, then you're going to speed up. If you any component that has a little bit of an anti-parallel, you slow down. But the force is perpendicular to the motion, then there's no change in speed. However, you have an acceleration. It's a non-zero acceleration. And by the way, this is a review for mechanics, which means that you have a change. So if you have a change in acceleration, is change in speed and change in direction. That means that in this case, this particle will turn this way without changing speed. Turn left to its motion. So again, that's how the magnetic force is applied. Okay, I can share the slide. Yeah, I'll share the slide. Let's see. So this slide is saying the same thing as I just wrote down. Magnetic force on moving charges, electric charges. Greatest force is applied when the moving charge is perpendicular to the magnetic field. And as you move more and more to the parallel, arbitrary. So if you are like this, and then if you're starting to move more and more like this, you have a less and less force applied, and then the force applied on the particle will be zero when they're completely parallel. So it could be parallel or anti-parallel, then you lose the force. Becomes completely zero. Even though you're moving, even let's say you have a very strong external magnetic field, there's no force applied. And how the force is applied on the moving charge is always perpendicular to its motion. So therefore, the particle, the moving charge, will never have a change in speed. It only changes its direction. Either it turns to the right or it turns to the left. That just depends on the direction of a moving charge and the direction of an external magnetic field. So here, right, in this case, it's again the electron beam that's coming out. So if you want to use the right hand rule, that you use the right fingers, these fingers is going to be the direction of a current. So that's going to be opposite to the direction of electrons. And then your palm, the direction of your palm, so you bend your fingers to the direction of your palm, and then north to south is going to be this way, and my thumb says the direction of a force. So this electron beam will feel the force upward. That's why it's going to go, after it's passing through this U-shaped magnet, passing through, it's going to start going upward without changing its speed. So that's how you see there's a magnetic force applied on a moving electric charge. Again, you don't have, if the electrons are stationary, again, no matter how strong the magnetic field you have, you're not going to have any magnetic force. Just keep sitting there. You can't accelerate it from rest. Okay. So the magnetic force in a moving charge can change the particles' only direction. Let me show you the video.
Here a large magnet. So I have here a large magnet, South Pole, North Pole, so the field is pointing up. And then I have a big, copper tube, which is connected to the wires here and there. When I connect these here, electricity will flow through this guy, through the red, through the copper tube, and then up through ground, and then back home. So we'll have electricity flowing this way, magnetic field pointing up. We expect a force inward. And sure enough, we get an inward force. Now, if I reverse the direction of the current, we expect an outward force. I'll get this guy out of the way. And there you see it, floating there. Because now that I've reversed the direction of the current is flowing this way magnetic field is pointing up, we expect an outward force. And that's what you say. Right-hand rule, simplified.
And this is also the one I wanted to show you. Same thing. So you see that these are, let me see, I need to cancel. When the wire is just inside without the current, if it's not connected to the voltage source, then you don't see no jumping in a wire. Just free electrons being there won't do anything. These free electrons has to be moving. Then as a current, then it feels a magnetic force, right? And also the direction, you can predict it. I want you to only know that the magnetic force applies perpendicular to the direction of motion. I'm not going to ask you if it's going to go up or down, but I need you to know if it's going to be either up or down, if it's moving in this direction or something. You understand? Like, I want you to know that a magnetic force is always applied perpendicular to the motion. I'm not going to ask you if it's going to turn left or right, but I want you to know that it's going to turn either right or left. It has to be, if it's moving like this, just going to move either this way, or it could be moving this way, perpendicular to the motion. All right, so applying all these things, magnetic force applied on the moving charge, and we say that if you have a current, electric current, so you have a moving charge actually generates magnetic field, which is electrodynamics, right? Electromagnetics. So you have electricity and magnetism that's combined together. Let's see that using those physical properties, we make something very useful. Here, electric meter. Let's say if you want to find out this wire or this orange wire in a slide, do they carry any electric current? How do I find out if there's a short or not? Then you can imagine to connect a wire and then loop it around, and inside the loop there is you put a magnetic compass. If you see any deflection in a compass, that means there is a current running. If you don't see any deflection of the compass, that means there is no current. So you have a short in a circuit. So that's how you can detect if there is a short or not. You can also find using a magnetic force to find how much current and therefore how much a voltage is running, right? So ammeter, voltmeter. Here you have a number of coils, and in the in the magnetic field, the north and south. So then depends on the number of, if you have a lot more coils running, then you have a lot of current running, then depending on the number of the current, actually, then the amount of magnetic force applied will be changed. So the magnetic force will be stronger with current, amount of current, how much current is running. And the magnetic force on the moving charge will be stronger if you have a stronger external magnetic field. So they use that idea to have a different amount of magnetic force applied, then it turns different amount. So you use that magnetic force applied on moving charge. How does the electric motor work? Electric motor. So you have an electric source, electric energy converts into mechanical energy that rotates around. So that means that you have so you can connect that a loop, like loop into the battery, and then there's a current flow. When there's a current flow, and then if you put it in between the magnetic field, it's gonna get deflected by the magnetic force, and it turns. The clever thing about this electric motor is that you see that in the socket, it says that there's a stationary contacts. There is a little slit in 180 degrees. So when this loop goes completely parallel to the magnetic field lines, then you lose the force and it will stop there. Or just that you're going to have inertia, but you're going to come back because the force is always going to be applied in the same direction. However, you have a big slit over there. So when it turns 90 degrees or this angle along with a parallel to the magnetic field, it disconnects momentarily and then it flips the direction of a current, voltage, plus minus to minus plus. So then now the force initially was applied up, it's going to be applied down and it changes the direction. And again, it goes anti-parallel. It disconnects momentarily, inertia, and it goes into up and down, up and down. That's why it can keep rotating. Otherwise, it's going to go like this and it won't pass there. So that's the genius, clever engineering that they did with having this slit over here. So using a magnetic force, electric motor can convert the electrical energy into mechanical energy by using magnetic force. Okay, and you will see that electric motor and electric generator. So now you crank up, right? I have this radio here that I can crank up. The handle comes out. And if I crank it, it can store some electricity. So that's the electric generator. Mechanical motion converts to electrical energy. And then electrical, in this case, electrical energy converts into mechanical energy. But those two, the motor and generator, they both work almost the same way. And we'll tell you, I'm going to discuss that in next video. Okay, so that's it for the last part of chapter 24. We have talked about magnetic force applies on a moving charge. Okay, see you in a discussion.